Okay. Hey, Bang, it's awesome to be here again. Let's talk about RAM memory. As most of you know, memory stores data as bits, zeros or ones. One will expect that if I write a 1 to the memory in certain memory location and then read again, I should get a 1, right? Unfortunately, software runs on top of hardware, and hardware can sometimes fail. One of the reasons of failure is called a single event upset. Single event upsets occur when a certain single particle, such as a cosmic ray, gets close to one of your electronic components and changes the electrical representation of a bit from 0 to 1 or vice versa. Single event upsets can occur at any time. However, there are some conditions that make them more likely to occur. Things such as high altitude, having a device with low energy consumption, or a device that's too old, or maybe a low quality power supply, or just being in a high temperature environment. Let's switch subjects. Oh no, sorry, I forgot. Well, these bit flips can cause some serious struggles in production systems such as a voting machine or even airplanes. Dangerous, right? Now let's change subjects. Let's introduce you to Shia. Shia is a contributor to a well-known piece of software whose maintainer has been kind of burned out these few months. So Shia offered to be in charge of releasing new versions of this software. After that, she realized that maybe she can tamper the contents of the executable files that get shipped to the users and maybe add some malicious content to them. That will be an interesting supply chain attack, right? Of course, that she doesn't want to be detected. So she can just replace the whole contents of the original file with a totally different malicious executable. She needs to be more clever than that. The other day, she had this revelation that maybe she doesn't need to replace the whole contents of the file, but instead she can just change a tiny part of the original file and then making the resulting binary malicious. Maybe she could just maybe she could just change a single bit of data. Think about that for a moment. Changing a single bit of data is literally the smallest possible change we can make to a binary. So that should be really difficult to detect, right? And even if someone somehow detected this, Shia could, since it's a single bit flip, Shia could just blame the cosmic ray for that. It wasn't me, it was the cosmic rays. Cosmic rays in your laptop, exactly during build time affecting the GCC process and flipping the exact bit that turns our executable file malicious. Yeah, you know, I'm a digital nomad, I travel a lot, so I think this last build was done while flying on an airplane at 30,000 feet. Maybe that caused the bit flip. Or maybe, yeah, I just used an old Raspberry Pi I had and a low quality power supply I found on a dumpster the other day. I built it with that, so maybe that caused the bit flip. Everyone just loves using old Raspberry Pis for production stuff and just pretending that's all right. Yeah. Or maybe, yeah, build time took so long to compile, I needed to do something else. So I just took my machine with me to the kitchen, started preparing some pizza, turned on my 800 degrees pizza baking oven, and maybe that could have caused the bit flip change. Look, my laptop is melted. It wasn't me, it was the cosmic rays. Of course, that for this attack to succeed, Shia will need to find the exact bit that turns the binary from a legit thing to a totally malicious one. This at first looks difficult, right? How can we change a single bit and cause so much damage to a system? Well, let's see that in a second. Let's introduce you to this piece of software some of you may have heard of sometime, called OpenSSH. This is the code. I don't know if you can see, okay? Well, this is the code used by OpenSSH to perform the public key authentication. This call to the SSH key equal function will check that the public key you use to log in is in the host machine's authorized key files. Otherwise, it will reject us. That code gets compiled to the following assembly. Can you see? Right? Okay. That assembly is just an instruction, a call instruction, a test that checks the return value of the function, and a conditional jump. If the function returns 0, that indicates failure. The test EAX will set the 0 flag to 1, and the jump if equal will be executed, and we will be taken to the code that rejects our login, and we won't be able to log in. Let's look at that jump if equal instruction for a second. That instruction gets encoded into x74, right? If we take a look to the x86 opcode table, we can see that by just flipping a single bit, we can transform that jump if equal instruction into a jump if carry. Since the previous instruction was a test instruction always set the carry flag to 0. So if we change the instruction from jump if equal to jump if carry, that means that jump to the code that rejects us won't be executed and will be logged in. Interesting. So, okay, I think we can have a demo. Okay, I have enough time. I think I should do this. Oh, can you see anything? Okay, I can see that. Oh, no, it's like this. Okay, maybe this. This is the attacker machine. This thing is the server will target. To simulate this attack, the idea is to manually change the contents of the binary file to pretend the supply chain attack existed. This technique could also be used, for example, by an attacker who wants to gain persistent access to a system, to a server, and then gain, to infect the system with this. So, to perform the demo, let's go here, or maybe, okay. If I'm the attacker and I try to generate an SSH key, of course, since that key is new, I can't just try to log in using that key I just generate with root to a server, right? Of course, I can't do that. Yeah. Okay, let's go to okay, were you able to see? Okay, right. Okay, this is the target server. Let's stop the SSH binary and perform some hexadecimal addition. Okay. 2, 4, 6. 1, 2, 4. In this position, there's that 74. If you remember, that's a jump if equal. Let's change that to a jump if carry. As we saw, let's start the service again, and if everything works properly, woohoo! Thanks. Built by the Cosmic Rays. Just a sec, okay. So, just to finish the session, let's have some conclusions. First, if you are developing some security-sensitive software, please invest on ECC memory. That's error-correcting code memory. That should fix most of the issues we show here. But second, and most important, if we want to take security seriously, we must take supply chain attacks into consideration. And if we want to prevent these supply chain attacks, we must have bit-for-bit reproducible builds that will enable us to detect any inconsistencies in the build time and prevent this and many other attacks. So that's the main takeaway I want you to get with. Reproducible binaries and bit-for-bit reproducible. Thanks.